Welcome back to Night Cosmos Sleep. Each night, the moon appears with the same familiar face, so quiet and unchanging that it is easy to believe this world has remained almost untouched throughout its history. Yet more than 4.2 billion years ago, deep beneath its cold gray crust, the moon's interior may have undergone a vast and profound upheaval. The phrase, "the moon turned inside out," does not mean that it reversed its rotation or began orbiting Earth in the opposite direction. What truly changed was the arrangement of the material within it. A layer of rock rich in iron and titanium formed near the surface, became too dense to remain there, and slowly began to sink, while lighter material from below rose to take its place. This process unfolded so gradually, silently, and over such an immense span of time that there was no single moment when the moon could be said to have turned over. No one witnessed this event, but its traces may still remain. They can be found in the titanium-rich rocks brought back by the Apollo astronauts, in the dark lava plains concentrated across the moon's near side, and in hidden linear structures detected beneath the surface through extremely subtle variations in gravity. Each clue tells only part of the story, but when placed together, they reveal a moon that was once far more active and complex than its motionless appearance suggests today. This internal reorganization may have influenced how the moon lost its heat, where magma found pathways to the surface, and why its two hemispheres became so dramatically different. One side contains broad, dark basalt plains and a thinner crust, while the other is brighter, more densely covered in craters, and almost entirely lacking vast seas of ancient lava. Even so, scientists still do not know exactly how long the process lasted, how much material sank into the interior, or how ancient impacts may have altered its course. This story also reveals something remarkable about the way science investigates worlds that cooled long ago. No camera existed more than 4 billion years in the past, and no single layer of rock has preserved the entire process from beginning to end. Instead, researchers must learn to read the surviving evidence in many different ways. The composition of a basalt sample can reveal what its source magma once contained. The shape of a dark plain can show how far lava once spread. Subtle changes in gravitational pull can indicate that denser or lighter bodies of rock still lie hidden beneath the crust. What makes this hypothesis persuasive is not one spectacular image, but the way separate pieces of evidence support one another. The bright crust suggests that lighter crystals once floated upward. Titanium-rich basalt points to a dense source material that later became involved in volcanic activity. Linear gravity anomalies are consistent with the remnants of rock layers that may once have sunk into the interior. When these individual stories converge, they form a history that can be tested, questioned, and continually revised. In the journey ahead, we will not view the moon as a completely dead sphere, but as a world that once separated into layers, became unstable, and reorganized itself from within. These processes moved more slowly than anything human beings could directly perceive, yet that very slowness allowed them to reshape an entire planetary body. A layer of rock needed to be only slightly denser, or one region needed to remain hot just a little longer, and over millions of years, those small differences could grow into structures that still survive today. Still, a degree of caution is necessary. The word overturn can suggest that the entire mantle flipped all at once, like a piece of clothing turned inside out, while the real process may have been far more fragmented and incomplete. Some dense material may have descended deep into the moon, some may have mixed along the way, and some may have remained at relatively shallow depths. That incomplete reorganization may help explain why the moon still contains distinct titanium-rich regions, and why its basalts do not all share the same composition. For this reason, the central question is not only whether the overturn happened, we also want to know where it began, how it spread, how deeply the sinking material traveled, and what influence it left on billions of years of later volcanic activity. These questions carry the story far beyond a single ancient event because they are directly connected to how a small world loses heat, preserves its internal structure, and records its own past. Before dense rocks could begin to sink, however, the moon had to pass through an even more violent stage. It first had to be born, melt almost completely, and form an ocean without water. Only by returning to a time when the surface did not yet exist in any familiar sense can we understand why the later layers of material were arranged in such an unstable order. To understand how a world that now appears motionless could once reorganize its own interior, we must follow the traces that remain in rock, lava, craters, and gravity. That journey will carry us back to an unimaginably distant time when the moon had not yet taken the familiar form we see in the night sky. About 4.5 billion years ago, the solar system had not yet settled into the stable, orderly orbits we know today. Young planets were still growing, countless enormous bodies of rock regularly crossed through space, and violent collisions could alter the fate of an entire world. Earth itself was not yet the familiar blue planet, because its surface remained intensely hot, was frequently struck by debris, and had neither oceans nor an atmosphere like the ones it has today. Within this chaotic environment, a body roughly the size of a small planet collided with the early Earth. This is the hypothesis most widely accepted by scientists to explain the origin of the moon. The impact released an immense amount of energy, blasting material from Earth's outer layers, along with matter from the colliding body itself, out into space. Rather than immediately falling back, this material formed a ring of molten rock, metallic vapor, and countless glowing fragments orbiting Earth. The space surrounding the planet would not have resembled the peaceful sky we see today, but instead a vast ring of fire moving through the darkness. Each fragment continued colliding with others, breaking apart, joining together, and gradually gathering under the influence of gravity. Over time, these pieces of material merged into an increasingly massive body, marking the beginning of the moon's existence. Yet, if we could have seen it then, we would not have recognized the cold gray object that now hangs in the night sky. The young moon had none of today's broad dark regions, silvery highlands, or countless overlapping craters. Many details of the moon's origin remain unresolved. The giant impact hypothesis explains several of its characteristics well, especially its relatively small metallic core and the close resemblance between lunar rock and material from Earth's outer layers. However, models must still explain why rocks from the moon and Earth are so remarkably similar in many of their chemical signatures. This has led scientists to continue testing different scenarios involving the angle and speed of the collision, the size of the impacting body, and the extent to which material from the two worlds became mixed. The early moon was also much closer to Earth than it is today. The smaller distance produced far stronger tidal interactions between the two bodies, and the sky above the young Earth may have been dominated by a moon that appeared much larger and brighter. Over time, energy transferred through tidal interactions caused the moon to gradually move farther away. But during those earliest stages, its close proximity made the heat and motion of the Earth-Moon system very different from what they are now. The moon may not have assembled in a single event. Many fragments could have first gathered into smaller bodies before continuing to collide with one another. Each impact added more heat, warming the surface and preventing the outer layers from solidifying too quickly. Even when a thin crust began to cool, newly arriving material could break through it and return molten rock to the surface. Inside the young body, radioactive elements left over from the formation of the solar system also contributed heat. They were not the only source of energy, but their decay helped the deep interior remain hot for longer. Together with heat from impacts and the compression of accumulating material, they caused the moon to pass through a period of extensive melting rather than quickly becoming a cold sphere of rock. Not every model suggests that the entire moon melted completely down to its center. Some scenarios allow the deepest regions to have remained only partially molten, while most of the outer layers formed a vast magma ocean. This distinction is important for understanding the structure of the core and mantle, but it does not change the central point of the story. A very large portion of the moon became fluid enough for minerals to crystallize, sink, or rise according to their density. Gases and rock vapor released from the magma may have formed a very thin and temporary envelope around the moon. It was nothing like Earth's stable atmosphere, but for a time, metallic vapor and volatile substances may have lingered above the hottest regions. As the moon cooled and its weak gravity proved unable to retain them for long, much of this lighter material gradually escaped into space or condensed back onto the surface. The loss of volatile substances left the moon drier and different from Earth, Yet dry does not mean completely devoid of water or hydrogen-bearing compounds. Studies of lunar samples and volcanic glass beads suggest that small amounts of volatile material may have remained trapped deep inside. These substances do not alter the main story of the overturn, but they remind us that the early moon was not a simple system made only of hot rock and metal. As heat gradually escaped, the glowing world began to shift from a stage of accumulation into one of separation. From that point onward, its history was no longer shaped mainly by fragments arriving from space, but by the interaction of materials within the moon itself. A vast magma ocean began to solidify, and within every crystal that formed, the future arrangement of the crust and mantle was quietly being written. At that time, the moon was a glowing red sphere, hot enough that most of its outer layers remained molten. Its light was not the gentle sunlight reflected from the surface that we see today, but may have resembled the reddish-orange glow of an enormous ember still holding its heat. The surface was never still, but changed constantly, as slow currents of molten rock moved and blended together. This heat came from the energy of the original collision, from the repeated impacts of material during the moon's formation, and from thermal energy trapped within the newly assembled body. The moon, therefore, could not cool immediately after its birth. Most of its outer region remained hot enough to form an immense expanse of molten material, not yet arranged into the clearly defined crust and mantle that would develop later. Had we been able to approach it, we would not have seen a solid, silent surface, but a world in constant motion. Bright and dark regions continually changed shape. Glowing currents drifted slowly under the influence of heat and gravity, and a haze of intense warmth covered the entire surface. The moon would have seemed to be breathing heavily with fire before gradually becoming a more stable world. What matters is not simply that the moon was once extremely hot, but that much of its outer region may have formed a global magma ocean. This was not a sea of fire in the familiar sense, but a planet-wide layer of molten rock surrounding the body. Within this environment, the moon's different components began responding to gravity and gradually moving toward positions that matched their densities. Materials that were heavier, lighter, faster to cool, or earlier to crystallize could not remain mixed forever within the same molten layer. Over time, they began separating from one another, opening the way for distinct layers to form inside the moon. Even while the body was still a glowing red sphere, the foundation for the overturn that would occur millions of years later was quietly being laid. Had the moon never passed through this nearly global period of melting, its internal materials could not have separated so clearly. There would have been no light crystals rising upward, no dense material sinking, and no iron and titanium-rich layer forming in an unstable position. The overturn whose traces we are following did not truly begin when layers of rock exchanged places, but at the moment the moon was born in fire. Looking at the quiet body in the sky today, it is difficult to believe that it once endured such a violent age. Yet beneath its cold gray crust lies the memory of a molten world, where rock had not yet hardened, and every component was still searching for its place. As the moon slowly began to cool, that ocean of stone entered a new phase, quietly separating its materials and preparing the interior for even deeper changes. On the young moon, there were no waves, shorelines, or long seasons of rain. Its first ocean was not made of water, but of molten rock spread across most of the surface. This layer of material may have been hundreds of kilometers deep, glowing red-orange in the darkness and moving continuously under the influence of heat and gravity. The idea of a magma ocean may bring to mind an enormous lake of lava, but the reality was far more extensive. This was not an isolated molten region on the surface, but the general state of most of the moon's outer layers after the body had formed. The rock had not yet had time to solidify into stable layers, so the entire exterior remained like a hot mixture moving slowly within itself. In the darkness of space, the moon began to lose heat. With no thick atmosphere to trap it, energy continuously escaped from the surface. Yet a world as large as the moon could not cool in a short time, because its deeper regions still held an immense amount of heat and continued transferring it upward. Cooling happened gradually, which meant the magma ocean did not solidify everywhere at once. Regions near the surface lost heat first, while the material below remained hot and in motion. Between these zones, matter was continually exchanged, slowly rising, cooling, and sinking again, like a current without waves that was never completely still. As the temperature fell, the first crystals began to appear within the ocean of molten rock. They did not all form at once, because each group of minerals could crystallize only when conditions became suitable. Some appeared fairly early, while others had to wait until most of the magma ocean had cooled before they could begin separating from the remaining liquid. The magma ocean was not a simple liquid with the same composition from top to bottom. Temperature, pressure, and the degree of mixing varied with depth, causing different minerals to appear at different times. In deeper regions, high pressure may have allowed certain crystals to become stable earlier, while rapid heat loss near the surface created temporary solidified zones. The entire system kept changing as crystals formed, separated from the liquid, and altered the composition of the magma that remained. Convection prevented the ocean of rock from immediately settling into completely motionless layers. Hotter material tended to rise, cool, and then sink again, carrying heat and chemical components with it. These currents may have kept crystals suspended for a time before they sank, or floated far enough to gather into clearly defined layers. The process of differentiation therefore depended not only on density, but also on the rate of cooling and the strength of internal motion. When a mineral crystallized, it removed certain elements from the magma while leaving others behind. Elements that did not easily fit into the structures of the early forming crystals remained in the liquid. Over time, they became increasingly concentrated. This is why the final remaining magma could become very different from the original mixture, even though both came from the same ocean of molten rock. The nearby presence of Earth may also have caused the two sides of the Moon to cool at different rates during this early period. The hemisphere facing Earth received heat from the still hot planet, while the far side faced the colder depths of space. Some models suggest that this difference may have contributed to the uneven development of the crust, although it is not the only proposed explanation for the contrast between the two hemispheres today. The first crystals to sink did not form a mantle resembling a single, uniform slab of concrete. They accumulated, became compressed, and may have trapped some remaining liquid between them. As new layers continued forming above, the older material below could still be altered by heat and pressure. The early mantle was therefore a developing structure, not a finished mass that became complete the moment crystals reached a certain depth. Despite this complexity, the overall result was the creation of reservoirs with different compositions. The deeper regions became rich in minerals that crystallized early. The crust accumulated lighter crystals that formed later, and the last remaining liquid retained many elements that had not easily entered the earlier minerals. These reservoirs would not remain motionless forever, but they established the initial conditions for every movement that followed. From a geological perspective, the magma ocean acted like an enormous sorting machine. It needed no gears or flowing water, only heat, gravity, and time. Every crystal that formed changed the machine slightly, until a world that had once been almost uniform became a collection of layers with different densities, compositions, and abilities to retain heat. As this process reached the stage of crust formation, the separation became most visible. Bright crystals, capable of floating rose upward, joined together into rafts of rock, and eventually formed the ancient highlands. Yet beneath this crust, the remaining magma was quietly accumulating heavier elements. The ocean created not only the Moon's first surface, but also the layer of material that would later make its interior unstable. The process can be imagined as a hot mixture slowly beginning to solidify. Components that crystallized more easily separated first, while the remaining liquid continued to change in composition over time. Because different mineral groups did not share the same density or properties, they did not remain in the same positions after forming. Some crystals were denser than the surrounding molten material and gradually sank deeper. Others were lighter and tended to rise toward the surface. This movement happened very slowly, but over enough time, it was capable of changing the structure of an entire world and making the Moon's interior far less uniform than it had been at the beginning. This was the first step in the Moon's division into distinct layers. Material that sank gradually formed the deeper regions, while lighter components moved toward the surface and prepared to create the crust. Between them, a vast mantle began to emerge, becoming the place where most of the Moon's rocky material would remain for billions of years. This separation did not happen as though differently colored liquids had simply been poured into a container. The boundaries between regions were not clearly defined at first, and material continued moving, mixing, and separating over a long period. Each stage of cooling allowed a new group of crystals to appear, gradually transforming the magma ocean from a molten mixture into a world with an internal structure. Once some minerals had crystallized and left the liquid, the remaining magma was no longer the same as before. Certain components had been removed, while substances that had not yet crystallized became increasingly constant. The magma ocean therefore did more than simply cool. Its properties changed continuously throughout its existence. These changes were essential because they determined which materials would remain deep inside the moon and which would move closer to the surface. Even a small difference in density could produce enormous consequences when the process continued for millions of years. Gravity did not need to act quickly, because it had enough time to pull heavier crystals downward and carry lighter ones higher. During this period, the lunar surface still did not have its familiar appearance. There were no dark basalt seas, no clearly defined bright highlands, and no countless overlapping craters. Instead, the outer layer was gradually closing, while beneath it remained a hot world where material continued moving and searching for more stable positions. The magma ocean was therefore more than simply a molten stage in lunar history. It was like a cradle in which the moon's entire internal structure began to form. From a mass of almost completely mixed material, the moon gradually developed a crust on the outside, a mantle below it, and deeper regions that retained denser matter. Although this ocean can no longer be seen, its traces remain in the composition of rocks at the surface. Bright highland regions, ancient rock samples, and the distribution of minerals all indicate that the moon once passed through a period of widespread melting. What remains on the surface today is only the cooled remnant of an ocean of rock that once covered an entire world. As the magma ocean continued to crystallize, most of the dense material gradually sank and helped form the mantle. Yet not every crystal followed that path. A group of lighter, pale-colored material began rising toward the surface, slowly gathering into the foundation of the moon's first crust. Within the deep red magma ocean, pale crystals began to appear. They formed as the molten rock slowly cooled, but instead of sinking like most of the denser material, they gradually rose. Tiny crystals floated upward through the hot ocean, gathered near the surface, and began creating the moon's first crust. These crystals contained large amounts of plagioclase, a mineral less dense than the surrounding molten material. Even a small difference in density was enough to send materials in opposite directions when the process continued for millions of years. While darker, heavier crystals slowly descended into the depths, the brighter and lighter ones continued rising toward the surface. Their ascent was nothing like bubbles rising through water. Molten rock is far more resistant to movement, so every change happened extremely slowly, almost imperceptibly over the span of a human lifetime. The moon, however, had millions of years to complete this process, while gravity steadily guided each component toward a position better suited to its density. At first, the pale crystals were scattered throughout the magma ocean. As their numbers increased, they began colliding, piling together, and forming larger floating clusters. These clusters gradually joined into broad sheets, like rafts of bright stone drifting across a hot ocean before merging into a layer that surrounded the moon. This floating material was not yet a complete crust like the one that exists today. It remained thin, uneven, and frequently disrupted by heat rising from below or by rocky bodies that continued falling from space. Even so, this was the first time the moon developed a solid surface broad enough to separate its molten interior from the cold emptiness beyond. Over time, the pale sheets of rock continued cooling, thickening, and becoming more tightly connected. Much of this material formed a light-colored rock known as anorthosite, which was widespread in the moon's primordial crust. Many of the bright highland regions visible today are believed to be remnants of that extremely ancient surface. Plagioclase was not the only mineral that appeared during this period, but it played a special role because it could float in lunar magma. Once enough crystals gathered near the surface, they formed a pale layer rich in aluminum and calcium, brighter than the darker rocks below. This became the foundation of the highland crust, one of the oldest components still visible on the moon today. The floating crystals did not arrange themselves into a perfectly flat surface. They could collide, rotate, be pulled apart by magma currents, and then gather again. Some liquid remained trapped between the crystals, leaving the young crust uneven in composition. As cooling continued, These pockets of magma crystallized and welded the fragments together, but they also created weaker regions that could later be broken apart by impacts. Some extremely ancient pieces of anorthosite are treated as rare windows into the time when the crust first formed. Their composition helps scientists test the model of floating crystals, although the apparent ages of these rocks may have been partly altered when they were reheated by major impacts. Determining exactly when the magma ocean solidified therefore requires comparisons among many samples and several different methods. The floating crust also changed the way the moon lost heat. Before it formed, the molten surface could radiate energy directly into space. Once solid rock covered the exterior, heat had to pass through a material that provided better insulation. The interior therefore remained hot for longer, while the temperature difference between the surface and the depths continued to grow. This allowed mantle rock to remain capable of slowly deforming, even after the exterior had become cold and rigid. Differences in crustal thickness between the two hemispheres may have begun very early, although later events made the contrast even greater. The impact that created the South Polaican Basin excavated deeply into the far side, while large basins on the near side were later filled with basalt. The crustal map we see today is therefore the product of both its original formation and billions of years of later change. While the crust was thickening, major impacts were still far more common than they are today. A sufficiently large body could break through the young crust, lift deep material toward the surface, and allow magma to erupt again. After each event, the damaged region had to cool and rebuild, turning the ancient crust into a mosaic of areas with different thermal histories. This helps explain why it is so difficult to find a perfect representative sample of the primordial crust. What remains has been crushed into loose debris, welded into impact rock, or buried beneath lava. Even so, the brightness of the highlands still reflects the widespread presence of plagioclay's rich material, strengthening the idea that light crystals once floated upward from the magma ocean. Just as the crust seemed to be closing, some liquid rich in elements that were difficult to crystallize remained trapped beneath it. This material occupied far less volume than the original magma ocean, yet it would have a disproportionately large influence on the moon's later history. The final liquid contained abundant iron, titanium, and heat-producing elements, creating a region that was both denser and capable of remaining hot longer than the layers below. The appearance of the crust was therefore not the end of the separation process. It merely marked the point when the uppermost region had become solid enough to preserve a temporary structure. Beneath it, the moon was still completing the final stages of crystallization, and those last stages would produce a layer of rock that could not remain stable in its original position. From Earth, the moon's bright regions are often most noticeable around the familiar dark plains. They are higher, older, and densely covered in craters because they have remained exposed for an immense span of time. Each bright area is like a surviving fragment from the period when the magma ocean began to close and the moon first wrapped itself in a crust of stone. While the pale crystals moved upward, most of the darker and denser minerals traveled in the opposite direction. They sank beneath the newly forming crust and gathered into a broad region surrounding the deeper interior. This region gradually became the mantle, where most of the moon's rocky material would remain for billions of years. The separation did not immediately create perfect boundaries. Some light crystals may have become trapped below, while part of the dense material remained near the surface. Magma currents continued moving, breaking apart the young sheets of rock and welding them together again. So the moon's internal structure developed through many stages rather than appearing in a single moment. Although the process remained chaotic, a new order slowly emerged. The pale crust lay on the outside, the darker mantle formed beneath it, and denser components continued moving farther inward. From an almost uniform sphere of molten material, the moon was becoming a layered world, with each region carrying its own composition and history. This crust was not equally thick everywhere. Measurements today show that the moon's far side generally has a thicker crust than the hemisphere that always faces Earth. This difference may be related to the way the moon cooled, how heat was distributed, and the major disruptions that occurred during its early history, although the complete explanation remains uncertain. What is clear is that the ancient crust created a new boundary between the surface and the interior. It acted like a lid of stone slowly closing over the magma ocean, making it more difficult for heat to escape and allowing the deeper regions to remain hot for a long time. Beneath the thickening crust, crystallization continued, and the composition of the remaining liquid kept changing. As more crystals left the magma ocean, the remaining liquid became increasingly different from the original mixture. Materials that had crystallized early were no longer present, while components that could not yet solidify became more concentrated. The final magma ocean was therefore not only smaller, but also richer in elements that had been less common in the layers formed before it. During this period, the moon seemed to be moving towards stability. A crust had appeared, the mantle was forming, and most of the ocean of molten rock had begun to solidify. Yet, this seemingly orderly arrangement created a new problem, because the last remaining liquid was not lighter than the layers beneath it. As the bright crust neared completion and most of the dense material had already sunk, a distinctive layer of rock began forming just below the surface. It contained more iron and titanium than the surrounding layers, making its position unstable. The moon seemed close to finding order, but the heaviest materials were still waiting in the final remnants of the magma ocean. The magma ocean had now been reduced to a thin layer of liquid beneath the newly formed crust. Most common minerals had crystallized one after another, separated from the molten mixture, and moved toward their own positions. What remained became increasingly concentrated, like the final sediment in a mixture slowly turning solid. Over millions of years, the composition of this liquid layer continued to change. Materials that crystallized easily had already departed, leaving the remainder increasingly rich in iron, titanium, and certain elements capable of retaining heat for longer periods. Although far less magma remained, its composition was distinctly different from that of the original molten ocean. The process can be compared to water gradually evaporating from a solution. What remains does not simply decrease in volume, but also contains a higher concentration of substances that have not been removed. Something similar occurred in the moon's magma ocean, except that instead of water and salt, it involved molten rock and heavy elements accumulating during the final stages. Within this last layer of material, a distinctive mineral began appearing in significant quantities. Known as ilmenite, it contained more iron and titanium than the minerals that had formed earlier. Because of this composition, ilmenite was highly dense and became an important part of the heavy rock layer located just beneath the ancient crust. From this point forward, we can refer to it simply as the iron and titanium-rich layer. It formed after the bright crust had floated upward and most of the mantle below had already developed. In terms of location, this layer lay relatively close to the surface, but in terms of density, it was heavier than some of the material located deeper beneath it. The final remaining liquid is often discussed alongside a substance known as creep, a name derived from potassium, rare earth elements, and phosphorus. It was not a single type of rock spread evenly beneath the crust, but a term describing a chemical composition rich in elements that did not easily enter the minerals that crystallized early. Creep is important to the moon's story because it is often associated with uranium, thorium, and potassium, elements capable of producing heat as they decay. The ilmenite-rich layer and the creep-rich material did not necessarily overlap perfectly, but both formed late in the solidification process. A region containing both dense material and elements capable of preserving heat would have been especially vulnerable to deformation. Heat made the rock softer, while its high density caused gravity to pull it downward. Together, these two factors created a structure resembling a heavy shelf resting on supports that gradually weakened over time. Models do not fully agree on the thickness of this layer. Their results vary depending on the moon's iron content, the depth of the magma ocean, and the extent to which crystals became mixed. A thin layer might sink in narrow streams, while a thicker one could form broad sheets. The shape of the overturn therefore depended directly on how the moon had crystallized beforehand. The instability was not caused only by heavier material resting above lighter material. The viscosity of the rock determined how quickly it could deform, while temperature determined whether it remained rigid or became more pliable. If the crust and mantle cooled too quickly, the dense material could remain trapped for a long time. If they stayed warm enough, even a small difference in density could grow into deeply sagging regions. A similar physical process is often called Rayleigh-Taylor instability. The name may sound complicated, but the idea is simple. When dense material lies above lighter material, the boundary between them tends to deform. places that sag slightly downward are pulled more strongly, causing them to sink farther and draw surrounding material along with them. At the same time, areas where lighter material rises tend to continue moving upward. On the Moon, this process occurred within solid rock rather than between two freely flowing liquids. For that reason, it may have taken millions of years. There was no sound, no sudden shaking, and no sharp boundary sweeping across the entire body. There was only continuous deformation, so slow that each generation of rock would have seemed motionless, yet powerful enough over time to exchange the positions of layers separated by hundreds of kilometers. As the first portions began to sink, they may have carried heat-producing material deeper into the interior. This caused the regions receiving the dense material to warm or cool more slowly. The overturn was therefore not merely the result of the Moon's original temperature, it altered its own environment as it unfolded. Sinking slabs may have created localized warm regions that later influenced melting. Simulation studies have produced different estimates of how much material descended. Some models suggest that most of the ilmenite-rich layer could have sunk deeply, while others leave a substantial amount at shallower depths. These differences do not mean the story is meaningless. Instead, they show that the available evidence is still insufficient to determine every detail of an event that occurred so long ago. What the models share is the conclusion that the titanium-rich layer could not easily have remained in its original position throughout the Moon's history. The structure contained an inherent imbalance that eventually had to be released. Once the first bands of rock began descending, they opened the way for a much broader exchange of material, in which rock could fall through rock without any empty space ever appearing. It was an arrangement that could not remain stable forever. In a stable structure, denser material generally tends to lie below lighter material. Yet, inside the young Moon, crystallization had accidentally placed a heavy layer of rock above less dense layers, like laying a wet blanket across a soft surface, unable to support its weight indefinitely. At first, the iron and titanium-rich layer may still have remained in place. The Moon's interior had not completely cooled, but the outer crust had begun to harden, creating a temporary barrier. For a time, the structure may have appeared unchanged, giving the impression that the Moon was approaching a stable state. Gravity, however, continued acting on every part of the body. It did not need to create a powerful pull or a sudden event, because geological time was long enough for small differences to develop into large-scale movement. The heavy layer above was continually drawn downward, while the lighter material beneath tended to move upward and take its place. Residual heat made this process easier. Although the Moon had already developed a solid crust when viewed from the outside, the deeper interior remained warm enough for rock to deform very slowly. These masses of material did not flow quickly like lava at the surface, but over millions of years, they could still bend, gather, and change position. The iron and titanium-rich layer therefore ceased to be a perfectly level sheet. Some regions became thicker, others grew thinner, and the weakest areas gradually sagged beneath their own weight. At first, the movement may have involved only slight deformation, but once the first portion began sinking, it pulled surrounding material with it and made the structure increasingly unstable. The entire heavy layer did not descend at the same time. Some regions may have begun earlier because they were hotter, thicker, or positioned above softer portions of the mantle. Other areas remained trapped near the crust for much longer, causing the overturn to proceed unevenly and leaving different traces beneath the surface. This variation is important because it may help explain why titanium-rich material is not evenly distributed across the Moon today. Some of it sank deeply into the mantle, some mixed with surrounding material, while another portion may have remained near the near side. The history of this layer was therefore not a simple journey from top to bottom, but a complex process unfolding through many stages. Heat-producing elements within the final magma also caused this region to cool more slowly. They did not generate unlimited heat, but they may have allowed some parts of the interior to remain warm longer than others. This kept the rock pliable and created favorable conditions for the dense layer to deform and begin its descent. By this point, the Moon had a bright crust, a vast mantle, and a deep interior, gradually becoming stable. Yet just below the crust, the iron and titanium-rich layer remained like a hidden flaw within an apparently complete structure. Everything looked quiet from the outside, while deep within, gravity was slowly preparing to rearrange the entire order. Remarkably, the overturn did not require another impact to begin. Its cause was already built into the way the magma ocean cooled and crystallized, when the densest material formed last but remained positioned too high. The same process that created the crust and mantle had unintentionally laid the foundation for the instability that followed. Under the combined influence of gravity, residual heat, and differences in density, the titanium-rich material began sagging more visibly. Its first portions slowly descended into the mantle, drawing surrounding bands of rock with them and setting a large-scale movement in motion. The moon had nearly completed its solidification, but its interior was only beginning its most profound upheaval. There was no single moment when the moon's entire mantle suddenly turned over. The process unfolded so slowly that, had we been standing on the surface at the time, we would have noticed almost nothing changing. Yet deep beneath the crust, the first portions of the iron and titanium-rich layer had begun to sag downward, like dark curtains slowly descending into the body of the moon. The idea of rock falling through rock may be difficult to picture, because in everyday life, stone feels hard, solid, and motionless, deep inside a world that was still hot. However, rock did not retain its shape forever. Under immense weight and high temperatures over millions of years, it could bend, deform, and move with the slow flow of an extremely thick material. This motion was nothing like lava spreading across the surface. There were no glowing red waves, no rapidly moving currents, and no empty space into which the material could fall. Instead, the dense rock pressed into the softer mantle below, while the surrounding material slowly shifted aside to make room. At first, the descending regions may have been no more than small depressions in the titanium-rich layer. Once one section sank slightly lower than the surrounding areas, gravity continued pulling it deeper, making the movement increasingly pronounced. From these weak points, the dense material began stretching downward in broad bands rather than breaking apart into individual stones. Modern models suggest that titanium-rich material may have descended as wide sheets or long, curtain-like streams, leaving remnants behind in the regions where the sinking began. This image is more consistent with a layer that once surrounded the moon than the idea of isolated blocks falling separately into its interior. As a sheet of dense material descended, it did not move through a perfectly still mantle. Ahead of the sinking slab, rock was pushed sideways or farther downward. Behind it, lighter material rose, possibly carrying heat upward from greater depths. These movements created slow circulation patterns, transforming the mantle from a collection of layered rocks into a system that was gradually mixing. Temperature may also have caused the overturn to occur in separate episodes. While the mantle remained hot, unstable regions could deform and sink more easily. Later, as cooling made the rock more rigid, movement may have slowed for a time. Yet material rich in heat-producing elements kept certain regions soft for longer, allowing them to continue moving even after other areas had nearly stabilized. Not every sinking slab traveled directly toward the moon's center. Horizontal motion within the mantle, variations in crustal thickness, and major impacts could have deflected them sideways. Some material may have become concentrated beneath the near side, while other portions descended at scattered locations. This deflection helps explain why traces of titanium-rich material are regional today, rather than forming an even ring around the entire moon. During its descent, ilmenite-rich rock may have reacted with the surrounding minerals. It was not a sealed mass, but could exchange material, partially melt, or be stretched into thin bands. After hundreds of millions of years, the original boundary between a sinking slab and the mantle may have become blurred, leaving behind a mixed region rather than a clearly defined layer. Some models suggest that the dense material eventually accumulated near the boundary between the core and the mantle. If so, it may have helped create a hot, dense, and chemically distinct region deep inside the moon. Such regions could have influenced how heat escaped from the core, how the mantle circulated, and how magma continued forming over long periods. The amount of material that truly reached this depth, however, remains uncertain. The overturn may also have altered the motion of the metallic core. The moon once possessed a stronger magnetic field than it does today, indicating that some mechanism inside it generated a magnetic field in the past. The sinking of dense material and the redistribution of heat may have affected heat flow across the core mantle boundary. Although the exact relationship is still debated, deep internal deformation did not leave direct cracks on the surface in the way an earthquake might. The crust may have responded only very slowly, while most of the evidence remained hidden in the composition of magma and the distribution of mass. This is why humanity had to wait for lunar samples and gravity maps before recognizing that such a large-scale process may once have occurred. What is especially remarkable is that the main phase of the overturn may have been completed while the moon was still very young, yet its consequences continued for billions of years. A redistribution of material lasting only a few tens of millions of years could determine where heat remained trapped, where magma formed, and where the surface later became dark. In planetary geology, an early event can often shape everything that follows. For this reason, the phrase "turned inside out" is not an exaggerated image of a single violent moment. It is a concise description of a series of slow, uneven movements that may not have ended in exactly the same way everywhere. As heavy slabs sank and lighter material rose, the moon changed from a simply layered body into a world with a complex, asymmetrical interior filled with distinct reservoirs of material. Every slab that descended produced movement in the opposite direction nearby. The lighter mantle material could not disappear, so it gradually rose to occupy the space left behind by the sinking rock. The moon therefore experienced not only downward movement, but also other streams of stone slowly rising within the same process. This is the true meaning of the lunar mantle turning inside out. The moon did not reverse its rotation, flip over in space, or move its entire interior all at once. What changed was the relative position of its rocky layers, as dense material moved deeper while lighter material shifted upward. The process can be imagined as a thick, heavy layer of mud resting on something softer beneath it. At first, the upper surface holds its shape, but over time, the heaviest regions begin to sink while the layer below is pushed upward around them. On the moon, the change happened far more slowly, but on a scale large enough to affect much of the mantle. The overturn did not occur evenly everywhere. Some regions may have been hotter, contained a thicker heavy layer, or rested above softer mantle, causing them to begin sinking earlier. Other places cooled more quickly or had a thicker crust that preserved the original arrangement for longer, allowing the process to unfold at different rates. As a result, not all of the iron and titanium-rich rock descended to the same depth. Some may have sunk deep into the mantle, some may have stopped at intermediate levels, while the rest remained trapped just beneath the crust. This uneven distribution later became an important clue for explaining why titanium is concentrated more heavily in certain regions than in others. As the dense sheets moved downward, they carried heat and chemically distinct material deeper into the moon. At the same time, rock from lower layers was lifted closer to the surface, causing materials that had once been separated to begin mixing. The overturn therefore changed not only the position of the rock, but also the way heat and matter were distributed throughout the interior. Some regions that were carried upward may have gradually cooled, while areas that retained more heat remained soft and capable of movement. This created a mantle far more complex than the original layered structure produced by the magma ocean. Instead of quiet rock layers arranged in order, the moon's interior became a system of sunken material, rising material, and regions still blending together. Studies of this process indicate that the unstable titanium-rich layer most likely caused an overturn on a broad scale. Scientists do not believe, however, that the entire mantle exchanged places in one perfectly organized movement. The surviving evidence is more consistent with an uneven process in which slabs of material sank at many different locations. The exact time required for the overturn to be completed is still uncertain. It may have unfolded through several stages, with the most unstable regions descending first while the remaining areas continued changing afterward. What matters is that the process occurred early enough to influence how the moon cooled, where magma formed, and how major differences developed across its surface. From the outside, the moon may already have begun to resemble the quiet world of stone we know today. Its upper crust was growing increasingly rigid, while the movements deep below produced no dramatic spectacle visible from space. Yet beneath the seemingly stable surface, countless heavy slabs were still descending through an upheaval that continued in silence. The overturn rearranged the moon's interior, but it did not leave the same result everywhere. Some regions retained more titanium-rich material and heat, while others became thicker, colder, and less active. The clearest signs of this imbalance would eventually become concentrated on the hemisphere that always faces Earth. From Earth, we always see the same familiar face of the moon. Broad, dark regions lie between bright highlands, shaping the human imagination across countless generations. Yet, when spacecraft first traveled around to the other side, the landscape looked almost as though it belonged to a different world. Even though both hemispheres were part of the same celestial body, the moon keeps nearly the same side facing Earth because the time it takes to rotate once is almost equal to the time required to complete one orbit. This does not mean the far side is always dark, because it experiences day and night just as the near side does. It is called the far side simply because people on Earth cannot see it directly. Before a spacecraft passed around the moon in 1959, humanity had never clearly known what the landscape on the other side looked like. The first images revealed a bright, heavily cratered surface almost entirely lacking the broad dark regions that form the familiar face of the near side. That contrast immediately became one of the greatest questions in lunar history. The dark regions on the near side are often called lunar seas, but they contain no water. They are basalt plains formed when molten lava flooded large impact basins and later cooled. Basalt reflects less light than the ancient highlands, so these plains appear as dark patches visible to the naked eye from Earth. The far side also contains some basaltic regions, but they are far smaller and much less common. Most of its surface is covered by ancient, bright rock and countless overlapping craters. NASA describes the far side as having a thicker crust, a heavily battered surface, and few of the prominent lava seas that dominate the near side. Crustal thickness may be an important part of the explanation. On the near side, the crust is generally thinner, allowing magma from deep below a better chance of rising through fractures and reaching the surface. On the far side, the thicker crust acts like a stronger lid of stone, making it more difficult for magma to break through even when heat remains below. A thin crust, however, does not create lava on its own. For dark maria to form, the interior must also contain regions hot enough for rock to begin melting. The moon's near side contains a broad area enriched in titanium and certain elements that can help preserve heat for longer periods, making its interior different from much of the far side. This region extends around Oceanus Procellarum, the vast dark area on the western side of the lunar face we commonly see. In scientific terms, part of this region is known as the Procellarum creep terrain, rich in potassium, rare earth elements, and phosphorus. These components do not turn rock into lava immediately, but they can help a region cool more slowly and remain internally active for longer. The contrast between the two hemispheres involves more than color. The near side has lower terrain across many of its maria, a thinner crust, and a greater concentration of heat-producing elements. The far side is generally higher, brighter, and retains a thick highland crust. These features are connected, but they cannot yet be arranged into a single chain of cause and effect accepted by every scientist. The Procellarum creep terrain is often considered a major center of this asymmetry. Spectral maps show that thorium and certain other elements are more concentrated there than across most of the moon. Because thorium is associated with materials that formed late in the crystallization of the magma ocean, its distribution suggests that the final liquid did not remain evenly spread around the entire body. The South Pole, Aitken Basin, is large enough to have affected the moon deeply. The impact that created it did more than carve out a vast depression. It also sent heat and shock waves through the mantle. Models suggest that material may have flowed toward the point opposite the impact, close to the near side. If creep and titanium-rich material was still soft enough at the time, it may have been drawn or pushed along by these currents. Still, we should not imagine that one impact swept the entire titanium-rich layer neatly to the opposite hemisphere. The process may have occurred gradually and in separate stages, long after the shock waves had passed. The impact created the initial conditions, while gravity and heat continued guiding the material for millions of years. The final result would have been a relative concentration, not an intact pile of rock beneath one hemisphere. Some far-side basalt samples are around 2.8 billion years old, while other evidence suggests that volcanic activity in the South Pole Aitken region began much earlier, compared with the vast maria of the near side. However, basalt flows on the far side remained far more limited. These samples therefore refine the question. The mystery is not why the far side had no magma, but why its magma so rarely formed broad plains like those of Oceanus Procellarum. The thick crust provides an obvious barrier. Magma may have formed at depth but lacked enough force to break through, cooling before it could reach the surface. On the near side, large impact basins further thinned the crust and created networks of fractures. Given the same amount of magma, the hemisphere with the weaker crust would leave more evidence at the surface. Temperature deep inside also played a role. Regions enriched in uranium, thorium, and potassium could retain heat for longer, increasing the likelihood of partial melting. If the near side possessed both a thinner crust and more heat-producing elements, the two conditions would reinforce one another. More magma could form, and it could also rise more easily, creating a cycle that continued through several stages. The Moon's asymmetry is therefore the result of an accumulated history. The magma ocean laid the foundation. The crust developed unevenly. The mantle overturned redistributed material, and impacts opened or closed pathways for magma. Each process explains only part of the story, but together they created two hemispheres so different that the contrast was immediately visible in the first photographs. From Earth, we happen to face the side with a clearer volcanic history. Its dark maria give the near side its familiar appearance, while the far side preserves more of the ancient crust. Tidal locking did not create this geological difference, but for thousands of years, it allowed humanity to see only half the story. Once spacecraft began orbiting the entire Moon, this asymmetry became evidence that the interior had not evolved uniformly. Titanium, creep, crustal thickness, and enormous impact basins all left signatures on the maps. Scientists came to understand that explaining the dark maria required connecting surface history with deep movements that had begun during the age of the magma ocean. Titanium is also heavily concentrated in many basaltic regions on the near side. This may represent material left behind from the iron and titanium-rich layer that formed near the surface as the magma ocean approached complete solidification. During the mantle overturn, most of this dense layer descended, but the process was uneven, and a significant amount may have become concentrated beneath the near side. Gravity signatures around the near side maria are consistent with the possibility that sheets of titanium-rich material once sank there. They do not prove that every part of the dense layer moved toward one hemisphere, but they suggest that the internal overturn may have left an asymmetrical structure. The Moon therefore differs not only at the surface, but also in the way material is distributed below. Another piece of the puzzle lies on the far side, where the South Pole Aitken Basin stretches across a large portion of the hemisphere. It is one of the oldest and largest known impact features in the solar system. The collision that formed it must have been powerful enough to penetrate deeply into the crust and disturb the mantle beneath. According to a model published in 2022, the heat and motion generated by this impact may have caused large-scale movement deep inside the Moon. Dense titanium-rich material and heat-retaining components may have been pushed or gradually directed toward the near side. Over time, this movement may have helped make one hemisphere richer in heat-producing material than the other. This remains an explanation based on modeling, not a direct image of what occurred. Scientists cannot yet say that the South Pole Aitken impact alone created the entire difference between the two sides. The model does show, however, that a giant collision can do more than carve out a basin. It can also alter the movement of material deep within a planetary body. The contrast between the Moon's hemispheres may therefore be the result of several overlapping processes. The far side crust is thicker, the near side contains more heat-retaining elements, the mantle overturned redistributed material unevenly, and major impacts continued redirecting the movement of rock. No single cause is sufficient to explain the full appearance of both sides. We can imagine the Moon as a sphere that cooled in two different ways. One side developed a thinner crust, retained more heat-producing material, and allowed magma to rise repeatedly. The other preserved a thicker crust, held on to more of its ancient highlands, and recorded impacts in countless craters that were rarely erased by lava. The dark regions on the near side are therefore more than traces of volcanism. They are the final result of a sequence that began with the magma ocean, continued through the mantle overturn, and may have been further directed by ancient impacts. Each dark basalt plain is a place where the moon's deep internal history found a path to the surface. The titanium-rich material that once sank did not disappear completely into the moon. Some of it mixed with the mantle, continued retaining heat, and later took part in the formation of magma. After hundreds of millions of years deep in darkness, this material began a new journey, slowly melting and finding its way back toward the lunar surface. After the deep internal overturn, the moon did not immediately become the cold, quiet world we know today. Large celestial bodies continued striking its surface, creating basins hundreds of kilometers wide and fracturing the crust on an enormous scale. The upper layers grew colder and more rigid, but far below, many regions of rock still retained enough heat to continue changing. Major impacts did not create all the lava themselves, but they left behind deep basins and networks of fractures extending through the crust. These weakened pathways allowed magma to rise from below. The lunar Maria formed later, when magma traveled upward through these cracks, flooded the floors of the basins, and solidified into vast basalt plains. Within the mantle, the iron and titanium-rich material that had once sunk did not disappear. Some of it descended farther, some mixed with the surrounding rock, while another portion may have remained concentrated beneath regions that retained heat for longer periods. When conditions became favorable, rock in these areas began to melt partially, producing magma that carried traces of materials formed during the age of the magma ocean. Titanium was not a fuel that powered lunar volcanism, nor was it the only reason rock began to melt. Its importance lies in the way it allows scientists to trace material from deep within the moon. When a basalt flow contains a high concentration of titanium, it suggests that the magma that formed it may have encountered or mixed with the iron and titanium-rich layer that sank during the mantle overturn. From hot regions within the moon, magma began to rise. It did not travel through an empty pipe like water flowing through a tube, but forced its way into fractures, pushed surrounding rock aside, and gradually moved closer to the surface. On the near side, where the crust was generally thinner and many large basins had already formed, this journey may have been easier than it was across most of the far side. Many lunar eruptions may have occurred along long fractures rather than being concentrated only around cone-shaped mountains. Relatively fluid lava poured out, flowed toward lower terrain, and spread across the floors of impact basins. Each new layer covered the one before it, gradually smoothing the landscape and burying craters that had already existed. While still hot, these lava flows may have glowed against the dark surface and spread across enormous distances. With no thick atmosphere to retain heat, their outer layers cooled quickly, while the material beneath took much longer to solidify. Eventually, the entire flow became basalt, a rock darker than the bright crust of the ancient highlands. This difference in color causes the basalt plains to appear as dark regions when viewed from Earth. Ancient observers believed they were bodies of water and called them seas, a name that remains in use today. In reality, they are immense fields of volcanic rock formed from many layers of lava that cooled during different periods. The magma that produced lunar basalt usually formed when only part of the mantle melted. This is important because the newly formed liquid did not have exactly the same composition as the rock that remained solid. Some elements entered the magma more easily, while other minerals stayed behind. Different degrees of melting could therefore produce different kinds of basalt, even when they originated in relatively nearby regions. Lunar eruptions did not produce the thick clouds seen around volcanoes on Earth because the moon had no substantial atmosphere to hold ash and gas. Lava erupted into a vacuum, while dissolved gases escaped very quickly. In some places, the release of gas may have sprayed tiny droplets of magma into the air, creating the orange or green glass beads later found in Apollo samples. These volcanic glass beads show that not all lunar volcanism consisted of flat basalt flows. Some eruptions were explosive enough to scatter fine material across the surface. The composition of these particles provides information about volatile substances and deep magma sources. They add another dimension to the story of the Dark Maria, revealing that lunar volcanism was more varied than its simple appearance today might suggest. The basalt seas also record changes in the rate at which the moon lost heat. Most large eruptions occurred while the moon was still warm enough for the mantle to melt frequently. Later, lava flows became smaller and less common. Samples returned by Chang'e 5 show that some regions remained active around 2 billion years ago, but these were exceptional areas rather than evidence that the entire moon was still as hot as it had been during its youth. In Oceanus Procellarum, the relatively young age of some basalt once raised questions about the source of the required heat. Samples about 2.03 billion years old did not contain unusually high concentrations of heat-producing elements, sufficient to provide a simple explanation. This suggests that mantle structure, mineral composition, and the way heat was retained may have been more complex. A region did not necessarily need enormous amounts of uranium or thorium to melt if its thermal history and composition were favorable. Titanium-rich basalt represents only part of the lunar maria. Some flows contain little titanium, while others have intermediate levels, showing that the mantle did not become one uniform mixture after the overturn. Distinct reservoirs of material survived and melted at different times. This diversity allows rock samples to serve as a chemical map of the moon's deep interior. Ilmenite may lower the melting temperature of certain mixtures, making titanium-rich regions more likely to produce magma when enough heat is available. This does not mean that ilmenite caused eruptions by itself. It only altered the conditions required for rock to begin melting. A source of heat, suitable pressure, and a pathway through the crust still had to exist together. As the basalt seas cooled and contracted, they developed grooves and folds. Some ridge-like features formed when lava layers were compressed, while long fractures could appear when the surface was stretched. These structures show that the maria were not simply passive fields of solidified rock, but continued deforming after the eruptions had ended. Volcanic activity eventually declined as the mantle became too cool to generate magma on a large scale. Fractures closed, magma chambers solidified, and the moon entered a quieter period. Yet this silence could not erase the composition of the rocks. Titanium, crystallization ages, and minerals continued preserving information about their deep sources, like a chemical message locked inside every crystal. When astronauts walked across the basalt plains, they were standing at the end point of a long sequence that had begun in the magma ocean. The rock beneath their feet had once sunk, mixed, melted, and risen again. Bringing samples back to Earth transformed those distant dark plains into material that could be weighed, cut, heated, and measured, opening a new way to understand the moon's internal history. The basaltic maria cover about 16% of the moon's total surface area, yet most of them are concentrated on the hemisphere that always faces Earth. That figure shows that volcanic activity did not cover the entire body, but left its clearest mark only in certain favorable regions. Across the rest of the moon, the bright ancient crust remains dominant, especially on the far side. One of the most prominent regions is Oceanus Procellarum, the vast dark expanse on the near side. Its name roughly means the ocean of storms, even though it has never contained water, wind, or clouds. It is more like a broad window through which the moon's thermal history and deep volcanic activity became visible at the surface. The dark maria were not created by a single eruption. Many basins were filled by repeated episodes of lava that may have been separated by millions or even hundreds of millions of years. Beneath a plain that appears smooth today, there may therefore be many stacked layers of basalt, each belonging to a different chapter in lunar history. Volcanic activity on the near side also continued longer than scientists once believed. Samples collected by the Apollo and Luna missions show that many basalt flows formed more than 3 billion years ago, while material returned by Chang'e 5 is about 2.03 billion years old. This result revealed that lava was still erupting on the moon hundreds of millions of years later than the limit previously established from older samples. This does not mean the entire moon remained highly active at that time. By then, most of the body had cooled considerably, and volcanism survived only in regions that retained enough heat or had crustal conditions favorable for magma to rise. Oceanus Procellarum was one of these unusual areas where basalt samples about 2 billion years old have been found. Titanium was not distributed evenly among these basalt flows. Some contained very little titanium, while others held exceptionally high amounts, showing that lunar magma did not come from a single source. Different regions of the mantle experienced different histories of mixing, melting, and cooling, leaving a distinct signature in each kind of rock. At Taurus Littrow, where Apollo 17 landed, very titanium-rich basalt dominates many of the collected samples. Some contain about 13% titanium dioxide by weight, a remarkably high proportion for basaltic rock. This indicates that the magma source below once contained large amounts of titanium-rich minerals, particularly material connected to the dense layer that formed near the end of the magma ocean era. Apollo 11 also returned a large rock sample identified as 10017. Classified as a high titanium ilmenite basalt, within the rock, iron, and titanium-bearing crystals lie among other minerals, like a chemical trace, frozen in place as the lava cooled. This sample became one of the clearest links between the dark plains at the surface and material originating deep within the mantle. We should not assume, however, that every titanium-rich lava flow was lifted intact from the ancient layer to the surface. Before becoming magma, the material may have sunk, mixed with the mantle, partially melted, and continued changing as it rose. The rocks found today are the final products of a long journey, not untouched copies of the original material. Lava flows also help reveal the relative sequence of events on the Moon. When basalt floods a crater and covers its floor, the lava must clearly be younger than the crater itself. Conversely, craters preserved intact on top of a basalt plain must have formed after the lava had solidified. Crater density therefore serves as an approximate clock. Ancient highlands are usually crowded with overlapping craters, while younger basalt plains are smoother and contain fewer of them. Precise ages, however, can be determined with greater confidence only when rock samples are brought back to laboratories and the time of their crystallization is measured. As the Moon continued losing heat, the regions capable of generating magma became increasingly limited. Fractures stopped carrying lava upward, the final flows solidified, and the dark maria became almost motionless landscapes. Yet their color, titanium content, and rock ages still preserve the history of a period that lasted for billions of years. The dark shapes we see each night are therefore more than patterns across the Moon's familiar face. They are the end point of a journey that began in the magma ocean, passed through the mantle overturn, descended into darkness, and later returned as lava. To understand that journey more clearly, human beings had to walk across those basalt fields and bring part of them home to Earth. An astronaut bends down on a plane of dark rock, uses a tool to pick up a small stone, and places it inside a sample bag. The rock looks little different from the countless fragments scattered around it, yet its journey began long before human beings existed. It was once part of magma deep within the Moon, rose to the surface, cooled, and then remained undisturbed for billions of years. When the Apollo astronauts set foot on the Moon, their goal was not only to prove that humans could reach another world. Every rock, every handful of soil, and every fragment they brought home had the potential to preserve part of a history the surface alone could not fully reveal. In laboratories on Earth, these small samples became gateways through which humanity could look deep into the Moon's past. Apollo 11 landed in the Sea of Tranquility, one of the dark basalt plains on the near side. Although the name suggests a calm body of water, the region is actually an immense field of volcanic rock. Lava once spread across this area, cooled, and formed the relatively level surface on which the astronauts walked. The samples collected there quickly revealed that they were not entirely like the rocks of the bright highlands. Many were basalts, formed when magma rose from deep inside the Moon, erupted onto the surface, and solidified. Some contained remarkably high amounts of titanium, like traces of a very different source of material hidden within the lunar mantle. Titanium does not make these rocks glow or give them an unusual appearance to the naked eye. Its value lies in what it reveals about the origin of the magma. When a basalt sample contains a high concentration of titanium, scientists can infer that the material from which it formed was once connected to regions of the mantle rich in iron and titanium-bearing rock. Apollo 17, the final mission to carry humans to the lunar surface, also collected many titanium-rich basalt samples. These rocks came from a region with a different geological history from the Apollo 11 landing site, yet they still carried evidence of a titanium-rich source deep below. When samples from several locations tell nearly the same story, the connection to the moon's interior becomes much clearer. Some basalt samples have been dated to about 3.6 to 3.7 billion years ago. This means the lava flows that created them appeared long after the moon had formed and its first crust had solidified. By that time, the body had cooled considerably, yet parts of its interior still remained hot enough to generate magma and carry it toward the surface. Apollo samples were sealed, numbered, and stored under carefully controlled conditions. Even decades later, some remain unopened so that future generations can study them with more advanced instruments. This has turned the collection into a lasting scientific resource, serving not only the questions scientists had in 1969 or 1972, but also hypotheses that emerged many years afterward. Every sample has its own context. The place where it was found, the surrounding terrain, and its relationship to nearby rock layers all matter. A titanium-rich rock collected from a basalt flow is different from a fragment thrown there by an impact from some distant location. For this reason, the astronauts photographed, described, and marked each site before collecting material, ensuring that laboratories received not only the samples themselves, but also the geological stories surrounding them. When scientists cut a basalt sample into a thin section, they can see how its minerals are interwoven. Crystal size reveals whether the magma cooled quickly or slowly, while the shapes and relationships among the minerals show the order in which they crystallized. Ilmenite appearing alongside pyroxene and plagioclase produces a structure different from that of titanium pore rock, helping researchers distinguish lava flows that came from different sources. Apollo samples also include breccias, rocks created when impacts shattered fragments of material and welded them back together. They may combine components from many locations and periods. Breccias are more difficult to interpret than intact basalt, but they provide information about the crust, material excavated from below, and ancient collisions. A tiny fragment inside a breccia can sometimes be far older than the rock surrounding it. Even lunar soil grains that seem like ordinary dust are highly valuable. They contain mineral fragments, glass particles, and material altered by the solar wind. Mixed among them may be pieces of basalt, anorthosite, or deeper rock thrown upward by impacts. Sorting through thousands of tiny grains allows scientists to expand their understanding beyond the few large rocks that are easiest to recognize. Most Apollo landing sites, however, were located within or near the basalt-rich near side. This created a clear sampling bias. Humanity gained highly detailed knowledge of several regions, but had almost no direct samples from the far side until more recent missions. Any global model must therefore avoid treating local characteristics as though they represent the entire moon. Samples returned by the Soviet Luna missions, and later by Chang'e 5 and Chang'e 6, have expanded the geological map. Chang'e 5 brought back basalt younger than many Apollo samples, while Chang'e 6 returned material from the far side to Earth for the first time. Each new location acts like another anchor point along the timeline, helping scientists test whether conclusions drawn from Apollo also apply elsewhere. Experiments that remelt titanium-rich rocks help scientists examine how magma may have formed. By placing material under temperatures and pressures similar to those in the mantle, researchers can observe which minerals melt first and whether the resulting liquid resembles Apollo basalt. These experiments cannot reproduce the past perfectly, but they can rule out scenarios that do not match the chemistry of the samples. Over the decades, the central question has shifted from "what are moon rocks made of?" to "how did those materials move through the lunar interior?" Apollo samples do not directly reveal a sinking sheet of ilmenite, but they do prove that titanium-rich material once contributed to the source of lunar magma. This is a necessary link between surface volcanism and the mantle overturn. When Grail gravity maps became available, the old samples suddenly gained new meaning. Gravity data provided the possible shapes of deep internal traces, while Apollo rocks supplied their composition. These two kinds of evidence were gathered decades apart, yet both point toward the same shared history, demonstrating the value of preserving samples and continuing to ask new questions of old material. A rock's age is recorded from the moment lava cooled and the minerals within it began to crystallize. This allows scientists to determine whether one basalt sea formed earlier or later than another. Small rocks therefore act like clocks that stopped at the exact moment the lava became solid. Beyond age, rock composition also helps researchers estimate where magma may have formed. Some titanium-rich basalts may have originated in regions approximately 200 to 400 kilometers beneath the lunar surface. This depth was not observed directly, but inferred from the rock's composition, the way material melts, and the conditions required to produce that type of magma. The journey from hundreds of kilometers below the surface did not happen in a single moment. Mantle rock first had to melt partially, after which magma entered fractures and slowly moved upward. Along the way, it could mix with other regions of rock, change in composition, and only then erupt onto the surface. A titanium-rich basalt is therefore not an intact piece of rock taken directly from the mantle. It is the final product of many stages, including melting, mixing, movement, and crystallization. The sample may preserve traces of its deep source, but it does not retain the complete form or composition of the original layer. This is much like looking at a river to learn about the mountains where its waters first began to flow, downstream. The water still carries minerals and material from distant places, but it has passed through many landscapes and blended with other currents along the way. Lunar basalt is similar, preserving traces of the mantle while having changed throughout its journey toward the surface. The Apollo samples helped confirm that the moon's interior once contained regions exceptionally rich in titanium. This fits the story of the final liquid left behind in the magma ocean, where iron and titanium became concentrated before the dense rock layer began to sink. Some of that material may have mixed into the mantle and then reappeared hundreds of millions of years later in volcanic magma. The rock samples also show that the dark maria did not form all at once. Some basalt flows are older, while others appeared much later, demonstrating that volcanic activity unfolded through many separate stages. The seemingly level surfaces of the lunar maria may actually consist of numerous lava layers stacked upon one another, each belonging to a different period. When compared with the brighter and more ancient highlands, Apollo basalts allow scientists to reconstruct part of the moon's geological sequence. The bright crust formed first. Major impacts created vast basins, and lava later rose to fill some of those depressions. Afterward, new craters continued appearing across the surfaces of the cooled basalt plains. Even so, Apollo samples came from only a limited number of locations, most of them on the moon's near side. They provide extraordinarily valuable information, but they do not fully represent every region of the lunar world. The far side, deeper areas, and many places that have never been explored may still preserve different kinds of rock and entirely different histories. Another limitation is that the astronauts could not drill hundreds of kilometers down to collect samples directly from the mantle. What they returned with consisted mainly of surface rocks, material excavated by impacts, and volcanic products that had already passed through many transformations. Apollo could therefore demonstrate that a titanium-rich source once existed, but it could not reveal the shape in which that layer descended. The rocks themselves cannot tell us whether the dense material sank as rounded masses, long streams, or broad curtain-like sheets. Nor can they reveal how much traveled into the deep interior and how much remained trapped near the crust. To answer those questions, humanity needed a method capable of looking beneath the surface without physically digging into it. Despite these limitations, the Apollo samples transform the way we see the moon. A small rock can connect the ancient magma ocean, the mantle overturn, and lava flows that emerged billions of years later. It reveals that the dark regions in the sky are not merely landscapes, but the final stage of a journey that began deep within the lunar interior. Apollo rocks confirmed that titanium-rich source material once existed and contributed to the formation of some basaltic maria on the near side. But to discover the shapes of rock layers still buried far below, scientists had to rely on a signal invisible to the human eye. That signal lies within extraordinarily subtle variations in the moon's gravitational pull. Two small spacecraft flew one behind the other around the moon, maintaining a relatively steady distance throughout their journey. When the leading spacecraft passed over a region containing more mass, gravity pulled it slightly forward. The distance between the two changed by only a tiny amount, but those seemingly insignificant movements were enough to reveal structures buried deep beneath the crust. The two spacecraft belonged to NASA's Grail mission and were named Ebb and Flow. They entered lunar orbit in early 2012 and flew in formation, one following the other along nearly the same path. The mission's goal was to map the Moon's gravitational field in unprecedented detail, allowing scientists to study the structure and history hidden within this world. Grail did not take pictures through solid rock, nor did it carry an instrument capable of looking directly into the mantle. Instead, the spacecraft continuously exchanged signals to measure the distance between them with extreme precision. Whenever gravity changed, that distance increased or decreased ever so slightly, like two leaves drifting through parts of a stream where the current moves at different speeds. We can imagine the gravitational field as an invisible fabric surrounding the Moon. Regions containing more mass produce a slightly stronger pull, while areas with less material or a thinner crust create a different gravitational effect. The spacecraft could not see this fabric, but their movements continually responded to every subtle variation along their path. As the leading spacecraft approached a region with stronger gravity, it accelerated slightly and temporarily moved farther away from the one behind it. A few seconds later, the trailing spacecraft passed over the same area and experienced a similar pull, bringing the distance between them closer to its previous level. By recording countless changes like these, scientists could assemble a vast map of gravity around the entire Moon. Grail's maps revealed that the Moon's gravitational field is far from uniform. Beneath regions that look similar at the surface, very different amounts of material may be hidden, while some impact basins contain dense masses of rock deep below. These areas of excess or missing mass can even influence spacecraft traveling in orbit. Topography also affects gravity, because a large mountain naturally contains more rock than a low plain. Scientists therefore combined gravity maps with measurements of surface elevation to separate the effects of mountains, craters, and basins from signals originating within the Moon. What remained helped them identify variations in crustal thickness and the density of deeper rock. Using this method, Grail produced the highest resolution gravitational map ever created for a celestial body by the time the mission was completed. Its data also showed that the lunar crust is generally thinner than many earlier estimates had suggested, with an average thickness calculated at roughly 34 to 43 kilometers. This result changed the way scientists understood the Moon's structure and cooling history. To measure the distance between ebb and flow, Grail used extremely precise radio communication. The spacecraft did not need to remain separated by an absolutely fixed distance. What mattered was knowing exactly how that distance changed over time. When a region of greater mass pulled first on the leading spacecraft and then on the trailing one, the signal between them recorded a distinctive rhythm of expansion and contraction. Millions of these tiny measurements were combined into a global gravitational field. Gravity reflects more than the density of rock. It also depends on surface elevation, crustal thickness, and the internal structure of impact basins. Scientists therefore created several kinds of maps by removing these effects one at a time. One of them resembles a Bouguer anomaly map, in which the influence of topography is reduced so that hidden masses below the surface become easier to identify. Large basins often contain positive mass anomalies known as mascons. Beneath a flat layer of basalt, there may be compressed crust, uplifted mantle material, or dense layers of rock. Mascons once caused problems for spacecraft because they pulled orbits away from predicted paths. Grail mapped them in far greater detail, turning a hazard of space navigation into a source of geological information. The linear anomalies associated with the ilmenite-rich layer differ from the rounded mascons of impact basins. They form an extended network around the procellarum region, suggesting a structure that existed before or beneath many visible surface features. Their many-sided pattern led researchers to compare them with boundaries, where sheets of dense material may once have separated and descended. Computer models begin with a dense layer positioned near the upper mantle. When this layer becomes unstable, sinking sections create concentrations of mass along lines or bands. The models then calculate what the remaining gravitational signatures might look like after the material deforms and the crust continues evolving. The resemblance between those results and Grail data formed the basis of an explanation published in 2024. Remarkably, these lines do not need to contain entire intact sheets of ilmenite. As long as some dense material remains more concentrated than the surrounding regions, the gravitational field can preserve a detectable signal. Over 4 billion years, the original structure may have been stretched and mixed, Yet even a small difference in mass was enough for the two spacecraft to sense from orbit. Grail also revealed that the lunar crust is more heavily fractured and disrupted than scientists once believed. Many deep structures are buried beneath impact debris and cannot be seen in ordinary images. This helps explain how magma once found pathways upward and how enormous basins altered the interior. The gravity maps therefore serve many scientific questions beyond the mantle overturn alone. Data from the two spacecraft were combined with topographic measurements from other missions, surface composition identified through spectroscopy, and rock ages determined from returned samples. No single dataset is enough to reconstruct the Moon's entire history. Yet when a gravitational line lies beneath titanium-rich basalt, is cut across by an ancient basin, and matches a model of sinking sheets, several independent pieces of evidence begin to fit together. The mission ended when ebb and flow were deliberately guided into a mountain near the Moon's north pole. Although the two spacecraft are no longer operating, their maps continue to be analyzed. New questions can still be asked many years later, just as Apollo samples remain under study with increasingly advanced instruments. Gravity is a unique kind of evidence because it cannot be hidden beneath dust. Lava may cover the surface, and craters may overlap one another, but mass still exerts a pull on anything flying above. In this way, Grail transformed the motion of two spacecraft into a method of listening to deep structures, bringing humanity closer to understanding the shape of the overturn without ever touching the mantle. Whether the crust is thin or thick determines more than the distance between the surface and the mantle. It also affects how easily magma can rise, how impacts deform the Moon, and how heat escapes from the interior. Grail's maps, therefore, became an essential piece of the story behind the dark basalt seas and the striking difference between the two hemispheres. Yet the data also preserve evidence of something far more ancient. When scientists examined the region surrounding the dark Maria on the near side, they noticed a network of elongated gravitational anomalies. These features do not appear as mountain ranges on the surface, but exist in the way mass is distributed beneath the crust. A gravitational anomaly does not necessarily represent a single intact object buried below. It may mark a region where the rock is denser than its surroundings, where the crust changes in thickness, or where an ancient structure once caused material to become concentrated. To understand the origin of these unusual lines, scientists had to compare them with different ways the lunar mantle may once have moved. In a study published in 2024, researchers combined Grail gravity data with models simulating the descent of titanium-rich material. The results showed that the network of lines surrounding the near-side Maria had a shape consistent with remnants left behind where slabs of dense material once sank. Together, these lines formed an almost polygonal pattern around the basalt-rich region. This fits the way the mantle overturn may have unfolded. The iron and titanium-rich layer did not necessarily break into small pieces that fell separately, but may instead have descended as broad slabs or long bands. As the dense material moved deeper, some of it left behind differences in mass at the places where the movement had occurred. Over more than 4 billion years, the original slabs may have deformed, mixed, and lost their former shapes. Even so, the gravitational field can still reflect part of the mass distribution they left behind. Like a fading footprint that still leaves a shallow depression in the ground, an ancient structure may disappear from view without vanishing entirely from the way gravity behaves. This is where Grail data differ from the Apollo rocks. Basalt samples show that titanium-rich material once existed and contributed to the formation of magma, but they cannot reveal the shape in which that material descended. Gravity maps provide a physical trace of broad sinking slabs, helping connect the rocks at the surface with movements that once took place within the mantle. Still, a gravity map is not a direct image of the overturn. The Grail spacecraft did not see curtains of rock descending, and the network of anomalies may also have been influenced by other events in lunar history. The 2024 findings are therefore understood as strong evidence supporting the model, rather than a complete record of exactly what happened. The strength of the explanation comes from the way several kinds of evidence point toward the same story. The magma ocean explains the origin of the titanium-rich layer. Gravity explains why that layer had to sink. Apollo basalts show that titanium-rich material later returned to the surface, and Grail detected linear mass patterns consistent with places where slab-like movement may once have occurred. The two small spacecraft completed their mission without drilling a single hole into the moon, simply by flying one behind the other and measuring minute changes in their separation. They allowed humanity to see beneath the dust, through the crust, and closer to an event that took place when the moon was still very young. Gravity became a form of invisible memory, preserved in the way rock remains distributed below the surface. Yet these ancient lines do not continue uninterrupted everywhere on the map. Some appear broken or altered where they cross large impact basins, like an old road cut through by a structure built much later. Those interruptions may help scientists determine whether the mantle overturn occurred before or after some of the greatest events in the moon's history. On maps of the moon's gravitational field, long lines lie deep beneath the crust and then suddenly fade as they enter a large impact basin. The pattern resembles an old road buried beneath a structure built later. The road must have existed first, while the structure covering it must have appeared afterward. The moon has no easily readable soil layers like those on Earth, nor does it have fossils that allow us to divide its history into distinct periods. Scientists must rely on rocks, craters, cooled lava plains, and extremely subtle variations in gravity. Each clue tells only part of the story, but when combined, they create a fairly clear sequence of events. Craters are the most visible markers. Whenever a large body of rock from space strikes the surface, it leaves a new scar across everything that was already there. If a crater cuts through a fracture or destroys an older region of rock, the impact must have occurred after the features it disrupted. The reverse relationship also helps establish the sequence. If lava flows into a crater and covers its floor, the lava must have appeared after the impact. By observing what lies on top, what has been cut across, and what has been buried, scientists can arrange many events in order, even when the precise age of each one remains unknown. This method of interpretation can also be applied to the lines hidden deep beneath the crust. They are thought to mark places where iron and titanium-rich rock once descended. When a large impact basin breaks or deforms one of these ancient lines, it suggests that the dense layer had already moved before the collision occurred. Several such lines are interrupted by extremely ancient basins on the moon's near side. This is a clue that the reorganization of the interior began very early, before many of the Great Depressions appeared at the surface. At that time, the moon was still young, and the deep rock within it retained a great deal of heat. From this sequence, scientists have concluded that the overturn took place more than 4.2 billion years ago. This does not mean they know the exact day when the first rock began to sink. It only indicates that the process must have occurred before certain ancient impacts whose traces still survive today. Determining relative age begins with a simple principle. A feature that cuts across another feature is usually younger. On the moon, this principle can be applied at every scale, from a small fracture to a basin thousands of kilometers wide. Interrupted gravity lines, basalt covering crater floors, and rays of debris lying across plains all create relationships of before and after that can be read. Crater density provides another way of measuring time. A surface that has existed longer usually accumulates more craters, while a younger surface has experienced fewer impacts. Scientists count craters of different sizes across a defined area and compare the results with regions whose ages have been measured from samples. This method cannot independently provide an exact age, but it helps estimate the ages of places from which no samples have ever been collected. Samples returned by Apollo, Luna, and Chang'e serve as anchor points for the crater clock. When the age of a basalt flow is measured in a laboratory, the number of craters on its surface helps calibrate the relationship between crater density and time. Chang'e 5's return of basalt about 2.03 billion years old was especially important because it filled a major gap in a timeline that had previously depended mostly on much older samples. For the mantle overturn, the most important clue is that some gravitational traces appear to predate ancient basins. If the lines formed as titanium-rich material descended and were later cut across by impacts, then the overturn must have begun extremely early. The age of more than 4.2 billion years places the event within a sequence, rather than assigning it an exact date recorded in a single rock. The beginning and end of the process may have been separated by a considerable span of time. One slab may have descended early enough to leave a trace before a basin formed, while another region remained unstable and continued changing afterward. The overturn may therefore refer to an entire period containing several phases rather than a brief event with clearly defined boundaries. Major impacts may also have destroyed older traces while stimulating new movement. Heat from a collision could soften the mantle locally, while the removal of crust altered the pressure below. A basin might therefore show that part of the overturn had already occurred, while also creating conditions that allowed material to continue moving afterward. The sequence of events was not always limited to two simple steps. The amount of material that descended may be better determined through global seismic data. Apollo seismometers operated only within a limited region of the near side. A new network spread across both hemispheres could measure waves traveling through the mantle, identify boundaries between materials of different densities, and locate unusual regions at depth. This would help determine whether titanium-rich material is concentrated near the bottom of the mantle, remains at intermediate depths, or is divided among many separate pockets. Samples from the South Pole Aitken Basin would also be extremely valuable. This region may contain material excavated from deep below and preserve evidence of how the enormous impact affected the mantle. Chang'e 6 opened the way by returning the first samples from the far side, but many other locations remain untouched. Every new sample could change the way we connect surface asymmetry with movement in the interior. Ultimately, the strongest models must explain several phenomena at once: the formation of the bright crust from floating crystals, the late appearance of titanium-rich material, the concentration of basaltic maria on the near side, the diverse composition of rock samples, and Grail's detection of hidden linear mass patterns. A model that matches one clue while contradicting the others cannot be fully convincing. Although gaps remain, the broad sequence has become increasingly clear. The moon melted, separated into layers, and formed a light crust with a dense titanium-rich layer above the mantle. That heavy layer became unstable and descended as slabs or bands, redistributing heat and material. Later, magma carrying traces of that material returned to the surface, while impacts and gravity preserved the order in which these events occurred. When we look at a crater, we are seeing more than the wound left by an impact. It is also a marker lying above or cutting through structures that came before it. Every crater rim, basalt layer, and gravitational line forms part of a clock with no hands, yet one that still allows us to read the passage of billions of years. The internal transformation may also have continued through several stages. Regions that were hotter and denser may have descended first, while other areas required much longer before they began to move. There was therefore no single moment when all the moon's internal rock layers changed position at once. We can imagine this as an old road covered by a building constructed later. We know the road came first, even if we do not know the exact day it was made. Gravity lines interrupted by impact basins establish the sequence in much the same way. Apollo rocks provide another kind of clock. When lava cooled, the minerals within it began preserving evidence of the time when they solidified. Some titanium-rich samples are about 3.6 to 3.7 billion years old, showing that this material was still contributing to lava long after the earliest overturn had occurred. The distance between those two periods reveals how long the journey of titanium-rich material may have been. It descended, mixed with other layers of rock, and remained deep in darkness for hundreds of millions of years. Only when certain regions began melting again was some of that material carried back to the surface in lava flows. The moon's gravitational field provides a third clock. Rock layers can be buried, lava can cover the landscape, and impacts can destroy the surface, but mass below still creates a gravitational pull. The two Grail spacecraft sensed those subtle variations and allowed scientists to trace structures that could not be seen. When all three kinds of evidence point toward the same story, the picture becomes clearer. The ocean of molten rock created the iron and titanium-rich layer. Gravity pulled that dense material downward, and later lava flows carried some of its traces back to the surface. Rocks, craters, and gravity complete one another wherever any individual line of evidence remains incomplete. This overturn also changed the way heat was distributed inside the moon. As dense material sank and lighter layers rose, heat no longer remained in its original locations. Some regions may have stayed warm for longer, while others cooled more quickly and became quiet much earlier. These differences may be connected to the greater abundance of lava on the near side. This hemisphere contains more dark plains, has a thinner crust, and retains more titanium-rich material. Yet this is not the only explanation, because major impacts and differences in crustal thickness also helped create the Moon's two distinct faces. A colossal impact on the far side may have set deep material into powerful motion and pushed some hotter rock toward the near side. This possibility is supported by models, but scientists still cannot confirm that it was the primary cause. The Moon's early history may have been far more complex than a single, simple movement. We also do not know how much titanium-rich material sank into the deepest interior. Some may have descended hundreds of kilometers. Some may have stopped along the way, while other portions may still remain close to the crust. This distribution may have determined where titanium-rich lava later appeared, but it cannot yet be observed directly. The original slabs of rock no longer preserve their former shapes. Over more than 4 billion years, they have been stretched, mixed, and altered by many other movements. The gravitational lines detected today are only the traces they left behind, like a faded footprint that still reveals that something once passed through. For this reason, we should not say that every detail of the overturn has been completely proven. The available evidence strongly suggests that the iron and titanium-rich layer once descended in broad slabs. The story is much clearer than it once was, but some parts must still be explored by future missions. Today, the ocean of molten rock is gone. Movement within the Moon has slowed, and its great eruptions ended long ago. The Moon now appears as a cold, dry, and almost motionless world. Yet that quiet appearance cannot erase what happened during its earliest age. The overturn remains recorded in the dark regions we see each night, in the Apollo rocks, and in minute variations in gravitational pull. Ancient craters stamped time across these traces, allowing us to determine which changes came first and which events followed later. From a glowing red sphere to a world with two very different faces, the Moon has traveled through a history far longer and more turbulent than its peaceful appearance suggests. Layers of rock once rose, sank, melted, and returned to the surface, leaving behind a record written not in words, but in color, location, and weight. Tonight, as the Moon moves silently across the sky, the dark regions on its surface remain the final chapter of a story that began more than 4 billion years ago. The surface has cooled and the volcanoes have faded, but deep within the rock, the memory of the time when the Moon rearranged its own interior has not entirely disappeared. Our imagined perspective slowly rises from deep within the Moon, passing upward through layers of cooled rock, through the pale crust, and beyond the fine dust covering the surface. From space, the Moon once again appears as a quiet gray sphere beside Earth, revealing nothing of the upheavals that once unfolded within it. There are no drifting clouds, no oceans of water, no forests, and no moving continents. The craters remain still, lava no longer flows across the dark plains, and the entire surface seems almost motionless. Yet this silence is only the final stage of a story that began more than 4 billion years ago. The Moon was born after a colossal collision during the chaotic youth of the solar system. Hot material was thrown into space, gathered together, and formed a glowing red world. At that time, most of the Moon's outer layers were still molten, creating a vast ocean of rock. Over time, that ocean began to cool. Bright, lightweight crystals floated upward and gradually joined together to form the first crust. Darker, denser materials sank, creating much of the deep rock below. The last remaining liquid, however, became rich in iron and titanium. It solidified into a heavy layer near the top, while lighter layers remained beneath it. This arrangement could not stay stable forever, because gravity continued pulling the denser material deeper into the Moon. Over millions of years, the iron and titanium-rich layer began to sag and descend into the interior. Lighter material rose from below to replace it, causing the rock layers to exchange positions through an extraordinarily slow process. This is the true meaning of the idea that the Moon once turned inside out. The Moon did not reverse its rotation or begin traveling backward around Earth. What was overturned was the arrangement of material deep beneath the crust. A world that seemed solid and immovable quietly reorganized its own interior. Some of the titanium-rich material that descended mixed with the surrounding rock. Hundreds of millions of years later, certain regions began melting again, sending magma upward through fractures. Lava flooded impact basins, cooled, and formed the dark regions we now see across the moon's near side. Those dark areas are not seas of water, but fields of solidified basalt. They preserve traces of material that once lay deep within the moon. In some rocks, unusually high concentrations of titanium offer a clue that their magma source was connected to the dense layer formed during the age of the molten rock ocean. When the Apollo astronauts set foot on the moon, they brought part of that story back to Earth. Small rock samples help determine the ages of lava flows, reveal the composition of magma, and show that extremely titanium-rich regions once existed inside the moon. Yet rocks can reveal where material has traveled without showing the exact shape in which it descended. Many years later, the two Grail spacecraft flew one behind the other around the moon and measured minute variations in gravity. From their motion, scientists mapped masses hidden beneath the crust. Unusual lines surrounding the dark maria were consistent with remnants of dense slabs that had sunk long ago. Craters and enormous basins helped establish the sequence of events. When a deep structure is interrupted by an impact feature, it suggests that the overturn occurred first. By combining Apollo rocks, craters, and gravitational measurements, researchers gradually reconstructed a story that began more than 4.2 billion years ago. Even so, many questions remain unanswered. No one knows exactly how long the overturn lasted, how much material descended into the deepest interior, or how much still remains near the crust. Colossal impacts may also have redirected the movement of rock, making the moon's internal history more complicated than we once imagined. Perhaps the most profound part of this story is not how many kilometers a layer of rock descended, but how a world preserves upheaval after its greatest movements have ended. On Earth, rain, wind, oceans, and moving tectonic plates continually reshape the surface. On the moon, the absence of these processes has allowed ancient traces to survive much longer, even though impacts and lava have still altered them. This is why one mission can complement another even when they are separated by decades. Apollo returned rocks, orbiters mapped composition and topography, Grail measured gravity, and Chang'e expanded the sample collection into regions that had never been represented before. No single instrument can see the entire history, but each illuminates a part that the others cannot reach. The overturn also reminds us that the stability of a planet or moon is only temporary. A layer of material may remain still for millions of years and then begin moving once temperature, softness, and gravity cross a certain threshold. Rock does not need to become completely liquid in order to change position. Given enough time, material that appears rigid can still flow, bend, and rearrange itself. This instability did not leave behind a simpler structure. Instead, it created a mixed mantle containing titanium-rich regions, titanium-poor regions, areas that stayed warm longer, and others that cooled early. This complexity produced different kinds of magma and allowed the moon's volcanic history to continue in changing rhythms. The moon's two faces are the greatest expression of this uneven history. The near side opened into vast basalt seas, while the far side preserved much of its bright highland crust. One hemisphere reveals where magma repeatedly broke through the surface, while the other retains more of the ancient crust. Both are necessary for understanding a world that developed asymmetrically from its earliest age. What we already know is enough to transform the familiar image of the moon. It is not merely Earth's companion reflecting sunlight, nor only the place where astronauts left their footprints. It is a world with a deep thermal, chemical, and dynamic history, one that experienced changes comparable to the great upheavals of the rocky planets. The dark regions visible each night are the result of many stages separated by hundreds of millions of years. Before basalt could spread across the surface, the titanium-rich material first had to form. Before that layer could sink, the magma ocean had to crystallize. And before the magma ocean existed, a colossal collision had to create the moon itself. Every shape on the surface is the endpoint of a chain of causes far longer than anything the naked eye can see. When sunlight moves across the rim of a crater, it illuminates only the outermost layer. Yet the past remains present in the way that crater cuts across the terrain, in the rocks it excavated, and in the gravitational pull of the mass below. The moon does not tell its story through sound. It speaks through overlapping layers, subtle differences, and signs that have taken generations of human beings to interpret. Perhaps one day, instruments placed deep beneath the surface will directly measure the remaining structures of those dense slabs. New rock samples may reveal that some parts of today's models are incomplete or incorrect. Science does not lose its beauty when a story is revised. On the contrary, every new piece of evidence makes the past more real and reminds us how much of the moon remains unexplored. Tonight, the moon's silence may carry a different meaning. It is not the silence of a world that never changed, but the quiet that followed after heat escaped, rock found new positions, and the final lava cooled. Beneath the silver dust, the entire structure still carries the consequences of movements that can no longer be seen. A world does not need to remain intensely active for its past to stay alive. As long as rocks preserve their composition, craters remain in the proper sequence, and gravity continues pulling spacecraft in its own distinctive way, those memories can still be read. The moon stands still, but its history has never been completely silent. What is clearest of all is that the moon was never merely a motionless gray sphere. It was once molten, divided itself into layers, sent material downward, and brought lava back to the surface. What we see today is only the quiet state that followed an age of upheaval lasting billions of years. A world can stand still and still preserve its memories. Those memories remain in the darkness of the basalt plains, in rocks carefully stored on Earth, and in the faint gravitational pull sensed by spacecraft. The cold, gray crust is only the final page of a story that began in fire and molten stone. Tonight, as the moon moves silently across the sky, the dark regions on its surface are still telling an ancient and extraordinarily long story. It is the journey of molten rock, of dense material sinking into the depths, of lava finding its way back into the light, and of a world that once rearranged its own interior before becoming Earth's quiet companion.